Thank you so much for taking some time out of your day today to join us for this webinar. Again, this is the Cannabis Testing webinar, Method Validation 101, hosted by Labstat and Labs-Mart. My name is Rachel, and I'm going to be your moderator for today. Before we begin, I'd like to give you just a quick overview of who Labstat and Labs-Mart are in case you've never done business with them before. Labstat and Labs-Mart are actually part of the Certified Labs family. So what does that mean for you? Across North America, their full-service laboratories provide comprehensive testing in food, tobacco, nicotine, cannabis, vape safety, dietary supplements, vitamins, and natural health products. This alliance creates a one-stop shop for all your regulatory requirements while offering a robust scope of testing services to meet your organization's sophisticated needs. From concept to final testing, their teams provide the scientific intelligence you need to ensure you're growing a world-class portfolio of products. Here in Canada, that means you can enjoy coast-to-coast locations with labs in both Alberta and Ontario. Their labs are GMP certified and ISO accredited. Of course, they guarantee fast turnaround times, and they're always updating their methodologies and instrumentation. Given what we're here to talk about today, it's important to note that the analytical methods used at Labstat and Labs-Mart have been validated and verified to be suitable for a range of matrices for both your cannabis and your NHP products and beyond. We're now offering these Learning Lab webinars every single month. They're always delivered by an expert and covering everything you need to know about analytical testing, packed with real-world information you can implement immediately. In October, we've got 2 webinars coming up. We'll be covering considerations when choosing a lab on October 14th, and laboratory accreditations, ISO, GLP, and GMP on October 28th. Follow us on Twitter at Labstat_INTL for more information on our upcoming webinars. So again, Cannabis Testing Method Validation 101. Our expert host for today is Devin Sears. Devin is the Director of Research and Development at Labs-Mart, and he's been tasked with the overhaul and modernization of the analytical methods they use to test cannabis products. As part of this effort, Labs-Mart has secured new instrumentation for pesticide analysis. They've overhauled their residual solvents method and are preparing to roll out an expanded terpene method soon. Devin is also responsible for method development and validation for natural health products, including vitamins, supplements, and herbal products. You can see there a whole host of highlights from Devin's career that clearly outline he is, in fact, the expert to talk about this topic today. Devin holds a BSc in chemistry from the University of Iowa, and he earned his PhD in physical chemistry from the University of Illinois at Chicago. So, without further ado, I will turn it over to Devin.
Thank you, Rachel, for the introduction, and welcome to all of our participants. We appreciate you taking the time out of your busy schedule to join us today as we're going to go through the aspects of method validation. What we will be covering today are a range of topics from method validation and verification, why validating a method is so critically important, what are the regulatory requirements, and what documents are necessary to capture validation activities. After this brief overview, we will walk through each of the required elements in a method validation and how they are experimentally determined. Finally, we will present you with some questions that you can take back to your laboratory to ensure that their methods are properly validated, thus ensuring the correct assessment of quality of your product. Today's presentation is meant to be a validation overview, so if there is a specific topic you want a more in-depth description or discussion on, please post a question and we'll cover it during the Q&A at the end. Okay, diving right in, what is method validation? Validation is a controlled exploratory process to determine a method's capabilities and limitations. During validation, a set of experiments are conducted following a protocol to assess the analytical method's capability to perform as expected and/or required. This assessment involves the interrogation of several attributes, also known as figures of merit. These parameters include accuracy, precision, specificity, linearity, limit of quantitation, limit of detection, range, and robustness. We'll go into each of these figures of merit in a few slides. But first, we need to ask a few questions about what validation is and why we do it. First, what is method validation? There are several reasons to validate an analytical method. First, through validation, a laboratory will gain a deep understanding of a method's capability and limitations. This understanding is critical to ensuring that when a method is used to assess product quality, the results are reliable, accurate, and true. The experience the laboratory gains with the method during validation will also lead to a better ability to predict how the method will perform when running new matrices and new samples. Method validation also provides vital information to assist in laboratory investigations by identifying the operating conditions under which the analytical method can reliably be run. Let's unpack that last statement. Based on the data collected during validation, the laboratory will have a detailed understanding of how the method's parameters, such as mobile phase compositions, gradients, temperatures, flow rates, injection volumes, etc., will impact the separation. This knowledge can then be applied during an investigation to determine if the method or instrument performance is the root cause of the suspect result. This is really the hidden power of a thorough method validation. The second reason for validating a method is detailed in Canada's Good Production Practices, or GPP, which requires that all methods used to test the quality of cannabis products be validated, thus establishing a regulatory requirement for method validation. Lastly, given that cannabis products are either inhaled or ingested, the use of validated methods is critical to ensure a true and accurate assessment of product quality, which is paramount to delivering a safe product to the consumer and ultimately safeguards your brand and your business. So now we have a basis for what validation is and why validation is important. The regulations require, and the regulation framework that requires validation. The next question is, are there specific elements that must be included in method validation? Turns out there are. As I stated earlier, under the GPP, Health Canada requires all test methods to be validated. The standards for validation adopted by Health Canada are those established by the International Conference on Harmonization, or the ICH. This organization was established to harmonize the regulatory framework and requirements in the pharmaceutical industry for critical activities such as stability, method validation, GMP manufacturing, and product development. The specific ICH guideline, Q2 Revision 1, or R1, establishes the requirement of method validation. The rest of this presentation will outline and detail the specific requirements of ICH Q2 R1. It should also be noted that the ICH has recently issued a concept paper to update Q2 in conjunction with the release of a new Q14 for analytical procedure development. However, since Q2 R2 is not official yet, we will not cover it in this webinar. Before we get started in the specific requirements of method validation, there are two additional questions that need to be answered. First, when is method validation necessary? And second, what types of analytical methods should be validated? To answer the first question, any method used to assess the quality of an input raw material, monitor and/or verify process control, or release and assess the quality of a final product must be tested using a validated method. Where multiple laboratories are involved, the methods shared between the laboratories must be validated in at least one of the laboratories and transferred to the second laboratory. Method transfers are not really in the scope of this webinar, but if you have a specific question around method transfers, I'd be happy to discuss in the question and answer section. Lastly, method revalidation may be required for methods that have undergone any change that could impact the performance characteristics of the analytical method. These method changes should be evaluated under the lab's change control procedures, which are part of their quality system. Part of this evaluation should be the impact the change will make on the validated status of the method. For example, if a flow rate is modified, the change in flow rate should be evaluated based on the potential impact to figures of merit such as the limit of quantitation, specificity, or linearity. Could the potential change in peak shape resulting from the change in flow rate impact the validation, both positively or negatively? If this impact is deemed significant, then revalidation should be conducted. It should be pointed out that these decisions should not be made in vacuum. In fact, they should be made in collaboration with the quality unit and not solely by the laboratory staff. The next question is, what types of methods should be validated? The ICH has defined 4 classes of analytical methods. The first are methods used to verify identity of a specific analyte in a sample. These are referred to as identification tests. The next are tests used for impurities and related substances, which has 2 classes of analytical methods. First is a quantitative method capable of quantitating these impurities over a range of concentrations, typically from the limit of quantitation to the upper limit established by linearity. Second is a limit test. A limit test is where a standard is examined at a predetermined level, the limit. Then a sample is examined and the response of the sample is either above or below that limit, resulting in a pass or fail. No quantitative information can be gleaned from a limit test. Lastly, are quantitative tests of the active compounds or active compound or compound of interest. Depending upon the complexity of the matrix being examined, the method can be combined, a quantitative method can be combined with an impurities or related substance method. However, if the matrix is complex, then the 2 methods may remain separate. Typically, compendial monograph methods for drug substances, for example, will separate out these 2 methods. Okay, now we're ready to get into the nuts and bolts of what method validation should look like. For the remainder of this webinar, I will be discussing figures of merit that should be investigated as part of the validation of a typical HPLC, GC, LCMS, or GCMS analytical method. I should point out that the ICH has specific guidance on figures of merit that are required for each type of analytical method. If you're interested in how to validate an ID test, for example, I would refer you to the ICH Q2 guidance document for further information. That said, for a typical chromatographic method, the following figures of merit should be interrogated under validation: accuracy, repeatability, intermediate precision, linearity, limit of detection, limit of quantitation, and specificity. It should be noted that method precision is established through the repeatability and intermediate precision experiments. Also, the method range is determined by the range over which you have linearity and accuracy established for both the analyte. So now we have our experiments that we need to run our validation. It's time to head into the lab. Not quite. First, there's some documents that must be addressed. The laboratory should have an SOP for method validation. This SOP should clearly describe the documentation and approval procedures necessary. At a minimum, validation must be conducted under an approved protocol. The validation protocol must describe the testing to be performed and the acceptance criteria for those tests. Well-written validation protocols will also provide explicit guidance on how samples are to be prepared for the validation. For example, a well-written protocol will not just declare that 5 concentrations must be examined to determine linearity, but will detail the target concentrations for each of the 5 points in the linearity. This will minimize the chance of failure during the execution of the validation, which ultimately results in re-execution, wasting time and money. On the back end of the validation, a validation report must be written summarizing the results of the validation experiments with a statement of the outcome of the validation. The validation report should provide the following, and I've got a disclaimer here that some of these are personal requirements that I require here at Labs-Mart. First, a summary of the validation data indicating a pass-fail status. Second, a section for each parameter validated discussing the outcome of experiments and a detailed tabulation of the data collected during validation. Third, a section detailing any deviations from the protocol or any acceptance criteria failures. Finally, fourth, a section making a final assessment of the method's validation status. Validation reports should be comprehensive and as close to standalone as possible. By standalone, I mean it has all of the data necessary to correlate that which is discussed in the previous 4 sections. I have personally written validation reports that are over 1,000 pages and describe the outcome of over 100,000 individual results. These are typically massive documents and provide a thorough description of the method's capabilities and limitations. So now with the documentation in order, it's time to actually head into the lab. In the next section, I will detail the experiments we employ here at Labs-Mart as part of our method validations. However, before getting into the validation experiments, I'd like to speak briefly about what we call pre-validation. During method development, the main objective is to optimize the analytical method to detect or quantitate specific analytes or analyte of interest. As part of this development, a lab should be assessing the method's likelihood of successful completion of validation. These quote-unquote pre-validation experiments are crucial in identifying potential shortcomings in the method. By addressing these issues prior to the execution of the validation protocol, the laboratory has a greater chance of success during validation. However, it should be noted the laboratory should have a process of documenting these method development and pre-validation activities to ensure that none of the pre-validation data results are included in the actual validation. Okay, finally getting to validation. To start, the first figures of merit we want to determine are accuracy and precision. But before launching into a detailed discussion of these two figures of merits, I want to review the differences between them as they are often confused. Accuracy is the degree of agreement between the result observed when running the analytical method and the true value. In the context of the figure on this slide, accuracy can be thought of as how close to the bullseye we get, where the bullseye represents the true value. In contrast, precision is the agreement between results obtained when multiple replicates of the test are executed. This is also referred to as the cluster in the data and is shown in the two bullseye patterns on the right. It is also important to point out that it is possible to have a method that is accurate yet not precise, and vice versa, precise yet not accurate. So let's start with accuracy. To get an intuitive feel for accuracy, take these two balances. We would expect that the balance capable of measuring to 6 decimal places, the balance on the bottom, would be capable of measuring a mass closer to the true value than the scale on the top, which can only measure mass accurate to the first decimal place. We can easily understand accuracy based on this simple analogy. However, measuring the accuracy of an analytical method requires a specific set of experiments known as a spike recovery. The spike recovery experiments will be detailed in the next slide. Another point to note, however, is that throughout this presentation, I will make reference to true value. It's imperative in a successful validation that you use a well-characterized and examined standards and reference materials, as these will act as the true values during validation against which all other measurements are compared. Now let's take a look at the experiment commonly used to determine accuracy. So the experiment at hand is called a spike recovery. Thinking back to the bullseye analogy from a couple of slides ago, to determine a method's accuracy, we have a bit of a problem. That problem is that we don't always know where the bullseye sits, so we have to design an experiment that allows us to choose a bullseye and see if we can hit it. This can be accomplished by an experiment called spike recovery. The left portion of this slide is a generalized schematic for how spike recovery experiments work. A spike, or sometimes referred to as a fortification, is the addition of a known quantity of analyte to a sample to test whether the response resulting from the spiked sample preparation is as expected. Because the response of the spike should be directly proportional to the amount of spike added, it allows us to verify that the sample matrix is not interfering with the method's ability to recover the response due to the additional analyte. So in this case, we can say that 1 + 2 should equal 3. Going into this experiment in a little more detail, we say we have a 1 milliliter sample containing the analyte of interest. Analysis of this unspiked sample results in an integrated response of, say, 1,000 milliAU from our UV detector. From our calibration curve, we can back calculate this to be a concentration of 1 milligram per milliliter. Now, if we were to spike in an additional 2 milligrams of the analyte of interest to this 1 milliliter sample, this should result in a 3 milligram per milliliter solution. When we run this quote-unquote spiked sample and we get an integrated peak response or integrated peak area of 3,000 milliAU, which from our calibration gives us a concentration of 3 milligrams per milliliter. We can now calculate the recovery of the spike experiment based on the recovery formula shown in the bottom right. The recovery tells us what percentage of the expected amount of the spike was measured or recovered from the spike sample, which establishes the accuracy of the method by demonstrating its ability to measure the expected or true result. Another way to visualize this spike recovery experiment is shown in the gauge charts on the left. In the first gauge, our sample is moved to 1 milligram per milliliter to represent the amount of analyte measured in the unspiked sample. In the second experiment, the spike sample, the gauge is moved to 3 milligram per milliliter. Taking the difference between these two results gives us a 2 milligram per milliliter gauge. This is our recovered result, which when divided by the amount spiked will give us a percent recovery. In this case, the recovery is 2 divided by 2, which is 100% recovery. A recovery of 80 to 120% is typically used to establish accuracy of an analytical method. These acceptance criteria are based on the generally accepted criteria for assay methods and impurity methods. Analytical methods that are used for trace analysis or have a limited dynamic range typically require wider acceptance criteria. In some cases, 50 to 150% can be acceptable. However, a larger acceptance criteria window should be well justified in the protocol. So what does a high recovery or a low recovery tell us? A low recovery is often the result of matrix interference. Particularly, it is a demonstration of the sample preparation's inability to fully extract the analyte from the sample matrix. This can also be the result of sample inhomogeneity, but the sample extraction is the most likely and should be ruled out first. A high sample recovery is typical result of sample homogeneity. This has an impact in that this is due to the fact that the concentrations of the sample used to make the unspiked solution has a slightly different concentration than the sample used to make the spiked solution. Sample homogeneity can be overcome through better sample preparation techniques. So to recap, a spike recovery experiment is a 1 + 2 = 3 experiment. Having established accuracy, now we can shift our discussion to precision. To get an intuitive feel of what precision is, we take these two instruments used to measure length. They both measure length with roughly the same accuracy. However, the calipers have been designed to perform measurements in a more repeatable manner. The use of the armatures to clamp to the object being measured in conjunction with the crosshatching used to read out the measurement leads to a significant improvement in the instrument's ability to repeatedly measure distance relative to the ruler. In method validation, we measure precision through two experiments, repeatability and intermediate precision. The repeatability experiment is akin to making repeated measurements of the diameter of a quarter with the caliper shown in this slide. Intermediate precision is a measure of how precisely two different people using two different calipers can measure the diameter of the same quarter. We'll go into more detail on how precision is measured in the next couple of slides. The first figure of merit to be evaluated as part of precision is repeatability. We have a rough feel for what repeatability is from the previous slide, but how do we measure repeatability in validation? Repeatability is measured by repeatedly running the method on a single sample and evaluating the spread of the data. Or to put it another way, 1 should always equal 1. So let's take a look at the experiment set up in this slide. The repeatability experiment, we have run the analytical method 5 times on the same sample containing a 1 milligram per milliliter of solution. As you can see, each time we obtain a result that is close to 1,000 milliAU UV response. In fact, the spread of the data is approximately 100 area counts with an average response of 998 milliAU and a standard deviation of about 37. But what does all that mean? To relate the magnitude of the standard deviation relative to the measured response, we need to define a new statistic, referred to as the relative standard deviation. The relative standard deviation is expressed as the standard deviation, or the spread of the data, divided by the average in the data set. In this case, the RSD is 3.7%. This can be thought of as the standard deviation represents 3.7% of the average response. Typically, repeatability is established with an RSD value of less than 5%. So here in this case, we've established repeatability. It is worth noting, repeatability is a measure of the variability in the measurement taken on a single instrument or by a single person under the same condition. Reproducibility measures whether the entire analysis can be reproduced in its entirety. Reproducibility can also be referred to as intermediate precision and will be discussed next. So the second figure of merit to determine precision is intermediate precision. Intermediate precision measures how closely the results are clustered when a sample is measured by different analysts on different instruments and sometimes on different days. In other words, is one always one when measured by two people on two instruments? So shown in this slide is a pictorial breakdown of how a typical intermediate precision experiment is carried out. In this example, the same 1 milligram per milliliter sample is prepared and analyzed by analyst 1 on instrument 1 and analyst 2 on instrument 1. That same sample then is measured by analysts 1 and 2 on instrument 2. The analysis of the results, so what happens here is all those results get pooled, and the analysis of those results then is very similar to the analysis performed for the repeatability experiment. Again, relying on the RSD to assess the intermediate precision. An acceptance criteria of 5% RSD, again, is a typical acceptance criteria for establishing intermediate precision. In this case, we see that the intermediate precision was measured to be a 4.1% RSD. As an aside, there is often a question of how variable a method is. The best measure of method variability is intermediate precision. So in this particular case, we would expect the method to vary by up to 4% when run analyzing samples over multiple days by multiple analysts on multiple instruments. The next figure of merit that needs to be evaluated is linearity. For the vast majority of analytical methods, we look for a direct relationship between concentration and detection response. That is, for every 1 unit change in concentration, we expect to see a proportional change in the response. The mapping of this response to concentration is what enables the analytical method to quantify how much stuff or analyte is in your sample. The most common detection methods, UV, mass spec, and fluorescence, all have this linear response to concentration. However, uniquely, the UV response must be linear within the limitations of the detector due to the Beer-Lambert law. This physical law stating that UV response is linearly related to concentration is what makes UV such a popular means of detection in LC. Looking at the figure in this slide, you can see that for each addition of 1 milligram to our 1 milliliter solution, we see a proportional response in the chromatographic peak area. When this response is plotted versus concentration, as is done in the graph, we see there is a linear relationship. To assess this linear relationship and provide a mathematical model, we can use a construct that we can use to construct our calibration curve. We rely on linear regression. Linear least squares regression, or linear regression, is the most common mathematical model used to assess linearity. This model works by determining a line that minimizes the error or distance between that line and the data points over all of the points in the fit. The resulting line can be described by two variables, the slope and intercept. The most common assessment of the quality of the linear fit is the correlation of determination, or the coefficient of determination, or R squared. This value is computed based on the errors calculated for each variable in the fit and the cross terms between those variables. The resulting coefficient can be interpreted as follows. If you achieve an R squared of 0.939, that means that 93.9% of the variation in the detector response can be explained by the variation in concentration. That said, R squared is not a perfect assessment of the quality of the linear fit. However, it is the only requirement spelled out in ICH-Q2. We recommend additional data analysis be performed to ensure that there is no bias introduced by the fitting procedure. For example, assessing the residuals of the regression line will highlight potential biases or shortcomings of the linear fit. Often the residuals show quadratic curvature if a bias or additional quadratic terms are missing in the linear regression model. The magnitude of these residuals will provide a gauge on how strong these biases are influencing the linear regression. Here at Labs-Mart, we have developed numerical methods to quantify the bias and identify points in a regression that should be omitted due to excess leverage or bias. If you have interest in these methods, please contact us and we can provide you with further details. The range over which linearity is established is very important. Linearity should be determined from the lowest level at which an analyte of interest can be accurately measured up to roughly 150% of the nominal or expected concentration. A minimum of 5 points over this concentration range should be assessed. That said, using traditional least squares regression analysis, a linear relationship can only be established over 3 to 4 orders of magnitude in concentration. Depending upon the unevenness of the variability in the measured response across the range of data, the data may need to be fit with a weighted linear regression. Additionally, one must consider the leverage of data points, especially at the upper end of the linear range. Leverage is a measure of how extreme values in the concentration will influence the regression results. In the last slide, I made reference to the method's linear range. At this point, it's important to define what the method range is. There are a couple of different ranges that we define during method validation. The linear range is the concentration range over which the calibration curve is linear. As can be seen in the figure in this slide, beyond the linear range, the response becomes curved and is no longer conforms to the linear regression line established in the previous slide. By contrast, the dynamic range is the range of concentrations over which there is a measurable response. Here again, the dynamic range is highlighted in the figure in this slide. Lastly, we need to define the method range. The methods range is the range that is reported in the validation report and is the range of concentrations for which the method has been demonstrated to be both linear and accurate. Typically, method range is established by running a series of spike recovery experiments at the low, mid, and high levels of the linearity curve to establish accuracy at those points. The next figure of merit is specificity. Specificity is a measure of the analytical method's ability to distinguish the analyte of interest from other analytes present in the sample matrix. From a chromatography perspective, specificity is determined by resolution, which is a measure of how well two adjacent chromatographic peaks are separated from each other. For reference, resolution can be calculated by the formula shown here. To give you some context as to what these numbers mean, a resolution of 1.0 represents 2.3% overlap in two adjacent peaks. A resolution of 1.5 represents a 0.15% overlap, and a resolution of 2.0 is considered to be completely baseline resolved. It is also important to point out that specificity applies not just to analytes, but interferences coming from the matrix as well. The acceptance criteria for specificity that is typically applied is a resolution of 1.5 or greater between the analyte of interest and the nearest peaks in the chromatogram. These criteria can also be applied to other peaks of interest or other impurities that are being validated as well. Now we need to define the lowest levels at which an analyte can be quantitated and detected. This is known as quantitation limit and detection limit, or sometimes referred to as QL and DL. The QL is the lowest level that an analyte in a sample can accurately be measured. As per the ICH guideline, there are 3 ways to determine QL. First, the lowest concentration where the signal to noise is greater than 10:1. Second, examining the error of the linear regression to mathematically determine a QL. And third, determining the lowest concentration that accuracy can be established through spike recovery experiments. The most common method for establishing QL is by signal to noise. In the figure in this slide, I show the signal to noise, how the signal to noise ratio is calculated. The peak height of the analyte is divided by the root mean squared of the noise over a specified noise region. That said, in my opinion, the better assessment of QL is a determination of the lowest level that a measurement can accurately be made. This is also how QL is determined at Labs-Mart. Measuring the QL in this manner ensures that any result at or above this level is accurate. The use of signal-to-noise or error of the linear regression does not provide solid experimental evidence of accuracy at the QL. The detection limit, or DL, is the level at which the method can reliably detect a signal. Again, this can be determined by signal-to-noise greater than 3:1 or examination of the error of the linear regression. Additionally, the ICH allows the DL to be established by visual inspection to determine the lowest concentrations where a peak is clearly visible over repeated injections. From a reporting perspective, numerical values should only be reported above the QL. Levels between the QL and DL should be reported as trace or less than QL, and levels below the DL should be reported as not detected. To wrap up the discussion of validation elements, I'd like to provide you with this summary table listing the required elements and typical acceptance criteria. These criteria are by no means absolute and may be varied based on the knowledge of the method gained during the pre-validation experiments and method development. However, large departures from these acceptance criteria should be well documented and explained in your validation protocol. A last figure of merit that should be discussed is robustness. Robustness is a systematic exploration of the method's limitations. In robustness, small variations to the method are made and the impact on the resulting chromatography is assessed. It is important to note that robustness is a validation element that can be determined outside of the protocol and does not need to be specified within the protocol. At a minimum, robustness should include a study to determine how long the standards and sample solutions are stable. Further examples of robustness would include small variations or perturbations of the mobile phase composition, temperatures, injection volumes, flow rates, and etc. from the validated parameters of the method. The impact of these changes should be assessed on the resulting chromatography to determine how much variation is allowed while still preserving the separation. The purpose of robustness is to provide assurances that the method will perform as expected, even if small variations from the validated method parameters are made in the laboratory. Okay, so we've gone through all the required elements in a validation. Now I'd like to speak briefly about how we approach validation here at Labs-Mart. It's important to recognize that a single analytical method cannot be developed to separate an analyte of interest in every possible matrix. To account for the highly variable nature of different matrices, we have employed a two-stage approach to our validations. We call it the validate and verify approach. Step one, we'll validate the analytical method following the requirements of ICH Q2 using a common matrix. In the second step, we verify the extraction of a new sample matrix or analyte from that sample matrix using the validated method. As part of this verification, we identify the figures of merit that can be possibly impacted by the sample preparation. This typically includes specificity and accuracy. We will then re-verify the specificity and accuracy as part of our verification process. So that wraps up the validation. The final step is to collect and analyze all the data and then write up the validation report. As stated previously, the validation report must summarize all the results, assess the results against the acceptance criteria stated in the protocol. Lastly, the report must make a final assessment of the method's validated status. Hopefully this introduction to the figures of merit measured during validation has provided some insight into the work being done by your lab to ensure their results are accurate, precise, and true. What I would like to leave you with is a small list of questions that you can use to initiate a conversation with your lab regarding method validation. These questions will probe how complete, compliant, correct and correct the validations are. The first question I would ask is, does the lab have a method validation procedure? The method validation procedure will establish that the lab has a recognized process of method validation, which ensures validations are performed in a consistent manner. The second is, was the validation executed under a protocol? Again, this is a demonstration of the lab's understanding of the regulatory requirements of method validation for GXP purposes. Third, were all 6 elements part of the validation? This ensures that the method has been fully explored under validation and is fit for purpose. Fourth, is there a validation report? This is the main documented evidence of the successful completion of the method validation. This should provide the complete account of what occurred during method validation and provide you a status of the validated method. Lastly, were all validation criteria met? This seems obvious, but in some cases, criteria could not be met and needs to be discussed in the context of the criteria failures impact on the method's validation status. So I know this seems like a massive amount of information in a very short period of time. Don't worry, you're not alone on this, and we're here to provide help. If you have any additional questions or concerns regarding method validation, please feel free to contact us. We will be offering a free 30-minute consultation to answer your specific question or concerns, with the offer lasting until October 15th. You can set up your consultation by contacting me directly at the email address provided in this slide. With all that said, I'd like to thank you for your attention. It has been a pleasure to spend time with you today and discuss a topic that I've been passionate about for the last 13 years. With that said, I'm now going to turn it back to Rachel to lead our Q&A. So give me just a second to unmute Rachel.
Thanks so much, Devin, and thanks for such a fantastic and in-depth presentation. Again, everyone, I know this is a lot to cover in a very short period of time. Devin could have done hours on this subject, I'm sure. So again, if you do have questions, reach out to Devin or hit us up on any of our social channels and we'll connect you with him as well. Don't forget, we have additional webinars coming up later this month. So mark your calendars and follow us on Twitter or LinkedIn for more information on those when the registration becomes available. If you do have a question, feel free to type it into the chat, which you can find just below on your admin bar in the Zoom window. And you can ask Devin any question that you like. Devin, do you see any questions popping up in your chat?
No, I do not at this point.
Okay, guys.
I do. How do these validations, or how do these validated methods transfer to microbial testing? Microbial testing is kind of a different beast in that you have, so you're validating the pathogens of interest for your particular matrix. So typically what's done there is you have a suitability test. So if you look at the USP or the United States Pharmacopoeia or even the European Pharmacopoeia, they would have requirements for what they call suitability. And this is where you show that the prescribed tests of the USP are suitable for your particular matrix. So there's not necessarily a validation, it's more a demonstration of method suitability.
So Devin, we have another question that says, do you know the Health Canada requirements for testing topicals?
I am not at this point very familiar with the requirements around testing topicals as far as what is actually required. At minimum, you will be required to verify the potency of the active ingredient in that topical. That potency method will need to be validated, and that validation will follow the guidance that I provided in this webinar.
Great. Any other questions?
Yeah, there was one. How do you apply these validations to different matrices? That is really our second approach. So once we have a validated matrix or a validated method, the way we view the matrice is how do we prepare that matrix such that the sample being delivered is consistent with what we validated the method for. So that really boils down to our sample prep. And then what we would do is verify that our sample prep is delivering a sample that is consistent with what we validated our method. So we would do that by conducting accuracy and specificity experiments using that sample prep for that particular matrix.
Okay, well, Devin, it seems that you did such a great job. Nobody has questions just yet. Or you've overwhelmed them so much they're not sure what to do next.
I have a feeling it's the latter.
Okay, folks, thanks again so much for joining us today. Again, if you have any questions at all, reach out to us online on any of your favorite channels. Drop us an email. Follow up on Twitter. We'd love to hear from you. Love to hear also if you have any other topics that you'd love for us to cover in these webinars, any burning questions that you have about analyticals testing for your cannabis or NHP products, please reach out and let us know. We want to make sure that we're providing you expert information that helps you move your business forward. So thanks again for joining us today, and we will see you on the next one. Have a great day, everyone.
Thank you.